Okay, dear students, so let's see what is there in this question. Very famous. I have seen this photo so many times now. Okay, a smoke detector uses the radioactive nuclide americium, whatever you want to call it, like 241 is the mass number for this. So it uses a radioactive nuclide. The americium is contained in a chamber that is open to the air. Alpha particle tracks, electrodes, americium source. Okay, there are two electrodes in the chamber that are connected to a power supply and a current sensor. Okay. The americium-241 emits alpha particles that ionize the air in the chamber. Okay. Each ionization forms one positive ion and one electron. Okay, so one positive ion is there and one electron is also there. These are called the ion pairs. The electrons and the positive ions move towards the electrodes and the sensor detects the current. Okay, no problem. When the smoke enters the chamber, fewer ion pairs are formed and the current in the sensor decreases, sounding an alarm. The decay constant of americium-241 is 5.08 10 per negative 11 per second. That is decay constant is also given. Okay. The chamber is 0.1 meter in each dimension. The nucleus of americium, again, I'm not able to pronounce this, 241 has 146 neutrons. Okay. This nuclide decays to Neptunium through the alpha emission. Okay. I don't know what those Avenger kind of things are happening here, who these superheroes are. Complete the nuclear equation for this decay. So I can do the mathematics behind it. Okay, no problem. So Armenium, the mass is 241, and it is given that it is having 146 neutrons. So number of protons will be 241 minus 146. So I'm just taking the help of my calculator. 146, and I'm getting 95. So 95 will be the atomic number. Alpha is always 4 and 2. So 2 reduce here, it will become 93, and 241 minus 4 is 237. So this is the reaction, and we have completed it. Quite easy. This principle is having a name which is Sodi-Fazan rule, but this rule, the name of this rule is not written anywhere. But this is known as Sodi-Fazan rule in nuclear science. Anyways, let us now move into the next question. Outline why the radioactive source is safer for use in a house. Why the radioactive source is safer for use in a house. Now that is a really big question. Let us think. Yeah, we can say that it is producing alpha, and alpha is not that having bigger life, like it can't move in the space for a very long time, and it dies very soon. So you can say that it will not be coming in contact with us, and that is why it is safer to use this radioactive reaction. Why? Because it is producing only and only alpha, which is not having that big life like that. Okay, so alpha is not that very dangerous. Why? Because it is not able to reach you. If it is able to reach me, then definitely it is harmful for us, but we will say that it is not able to reach us. Now, deduce whether the radioactive source, I will show you the mark scheme and we will see what IB has written. Okay, deduce whether the radioactive source will need to be replaced during the life of the detector. So whether it will be needed to be replaced. Do we have that kind of an information here? Okay, so in the question, nothing is given. The mass of the material, that is americium-241, is not given. How much mass are you using? So the only method that we can find here is that the decay constant is given to me. So what I do in this question, I would be finding the half-life. Okay, so the decay constant is 5.08. Let us find the half-life for the material. So half-life will be ln2 divided by 5.08 into 10 raised to power negative 11, and this value should be coming like 0.693 divided by 5.08 into 10 raised to power 11. That is too much. Okay, so this value is coming out to be 1.36 into 10 raised to power 10 seconds. So 10 raised to power 10 second is too much a value. These are many seconds. How many hours does this make? 3600 second in 1 hour. So it comes out to be too much. And divided by 24 hours, let's say, divided by 365 days, yeah, nearly 432 years. It means that whatever material that you have, whatever material, the quantity that you were using, whether it was lesser or whether it was more, in 430 years it will reduce to 50%. The rest 50% will, even then it will be there, so you can't say that it will be over. So 432 is a very big life, so I don't think anybody is going to survive for that much of the time. So clearly we need not to replace the radioactive material inside of that. This is the rationale that we can give here. Okay, so this is over. Now moving next, the initial activity of the source is 42 kilobecquerel. So the initial activity is 42 kilobecquerel. What is this becquerel? So dear students, becquerel is the number of decay taking per second. So if 42,000 becquerel, it means 42,000 decays are happening in 1 second. 33% of the alpha particles emitted by this source enter the chamber and form an ion pair. So only 33% of the alpha particles. Okay. 33% of the alpha particles. Each alpha particle has an initial kinetic energy of 5.5 mega electron volt. Okay, so the initial activity is 42 kilobecquerel. It means that 42,000 decays are happening in 1 second. So one decay will be producing one alpha particle. So how many alpha particles do we have? 40,000 alpha particles. But only 33% of these alpha particles are used in creating the reaction, isn't it? 33% of the alpha particles emitted by the source enter the chamber and form the ion pair. So these many electrons are created, these many ions are created. Okay, one positive charge and one negative charge. Each alpha particle has a kinetic energy of 55.5 mega electron volt. The energy required to form one pair is 15 electron volt. So okay, so it means these many number of alpha particles are there. So one alpha particle is producing many ionized particles. It's not that one alpha particle is ionizing one nuclei. No, it is ionizing many nuclei in just one go. But how many nuclei are being ionized? Let's see. So the total energy with the alpha particle is 5.5 mega electron volt, and for one you need 15 electron volt of energy. So how many electrons can be produced, or how many ions can be generated? This many number of ions can be generated there by one. So how many alpha particles are there? These many. So we can multiply this with 5.5 into 10 raised to power 6 divided by 15. So what I did, listen to me, 42,000 are the alpha particles which are actually generated. Out of this, only 33% of the particles are participating in the reaction. And these 33 particles, one particle is able to produce these many ions. So these many alpha particles will be producing, when you multiply this with this, these many total ion pairs. So this is the total number of ion pairs produced. Total number of ion pair produced is this. Okay, now this is the total number of ion pairs. So these many electrons are there, these many positive ions are there. Now the question is, calculate the maximum current in the chamber due to electrons. They are not talking about the total current. See, the current will be there because of the positive ions as well as because of the negative ions. Like this is the chamber, this side is positively charged plate, this is negative plate. So the electrons will be moving towards the positive charge and the ions will start moving towards the negative charge. So if you try to find the total current, then we have to find what is the total number of like the charge here and this also. So we will be multiplying it by 2. Okay, because in one ion pair there is one electron and one positive charge, so they are moving in opposite direction. So current is because of electron as well as because of the ion. But the question now is asking only for the electron, so we are not multiplying 2 here. So these many electrons are there which are moving from one plate to another, and we are only concerned with the electrons. So these many electrons. So what is the total current? So this is the number of electron. Okay, this is very long question. Number of electrons is multiplied by a charge on one electron. So this is the total charge which is transferred by electrons from the negative plate to the positive plate. And in how much time? Everything is happening in 1 second. So we are going to divide this everything by 1 second. So it not to be written here because 1 is just 1. So this is equal to the current which is produced by electrons. We are not considering the current which is created by the positive charge, that we are not considering here. If we would be considering that also, we will multiply 2 into this. So actually the reading of ammeter will be double than this, but the question is not about that. Okay, so be very careful and you can find this value. Let me plug this value in my calculator and find it, and we will verify from the mark scheme also. Well, I'm finding a very low current, and the value of the current is 8.1 into 10 raised to power negative 10 amperes. Okay, dear students, so let's see if this value is correct from the mark scheme. 8 into 10 raised to power negative 10. Well, absolutely correct. So these are the answers here. So our first answer, this is correct. The alpha particle only travel few centimeters, and that is why it will not even escape the chamber. Half-life is given, yes. So that is the correct reason. And here we have done the same thing, and we are getting the same value. By the way, I am getting the value as 8 point something into 10 power negative 10 amperes. So for them, it is 0.8, like 10 is taken, and it will be negative 9 amperes. So we are getting exact answers here, exact values here. This is how we do this question. Okay, dear student, thanks for watching this video. This is Professor Varun. All the best for your exam. Bye.